discuss how to develop a full adder using two half adders. So I select a new project here. So in the new project, I'm going to select the name of the project as FA, and here I select the next. It's you want to do you want to select a different project directory? No, I'll just select it. Then I go for the empty project and select the design files you want to include to add all design files in the project directory to the project. Okay, so what do we do here? Since we are going to make use of the half adder program, so we are just going to make use of the half adder program that we already written here. So I just taken here, then I select next. So here I change the family to max 10 device. Then I select next. So here in the simulation, I select the model sim Altera and Verilog HTLS come up by default. Then select next. So now if you look into it, my top level design entity is going to be full adder, and then I finish it. So as soon as I finish this, now I can open a new text file, that is a Verilog HTML file. So here in the Verilog HTML file, I'll be able to write my Verilog code here. So what do I write? I write Verilog code for full adder. So now I just type my module. We have given a name FA. Then output of this modules are going to be sum comma carry. Then input are going to be A comma B comma Cin. So that is for the interfaces of full adder. Then end module. So within end module, we are going to write the necessary statement. So to develop a full adder using two half adder, I need some additional signals. So I declare the additional signals here as S1, C1, and C2. These are the additional signals over here. Then already we know that our module is going to be internal module is going to be HA, and the name of the primitive are given as HA1. Then the output of the first HA will be the sum. That will be the sum of the HA half adder is given to S1, and it takes then the carry for the first half adder will be C1. So this is generated by accepting A and B as the input. It's also we use another half adder here, that is half adder, that is named as a half adder 2. Then the sum of this half adder will be directly the sum output, whereas the carry of this half adder will be C2, will be C2, and the input for this half adder will be S1 and S1 and Cin. S1 and Cin are the inputs for this half adder. So that is for the second half adder. Now, what do we get next? We have to OR the two carries. So we are going to OR the carries. So OR get also I named it as R1. Then the output of the R is nothing but a carry of the full adder. Then the inputs for these R are going to be the C2 1 and C2. C1 and C2 are going to be the input. So this basically defines the full adder for full adder using two half adders. So we'll save this. So if you want, you can save it in separate file, or we'll just better create a new folder which is called FA. So inside FA, I'm just going to put this file FA fa.b and adding it to the current file for the project. So that's also it's added over here. Then what do? We go for elaboration, that is analysis and synthesis. Here we have a sub process called analysis and elaboration. So we're just going to start this. So as we start this, it checks with the top level entity name, that is FA, and internally we have used two modules half header. So you can see the elaborating entity HA for hierarchical definition for half header. Okay, now here if you want, I think I named it here as here also HA1 and HA2. Okay, fine, no problem. So next what we do, we go on to search for our simulation. So here we have a simulation and we run the RTL simulation. So in the RTL simulation, we are going to check, are we getting our expected output. So now here in this, we just expand the library, and here we expand our work. So which one we are going to simulate? We are going to simulate the full adder. So we are going to simulate it. So now the full adder consists of the two half adders and the OR gate. That's clearly it's described here. Then in the objects, we have the signals. I don't want to take all the signals. Instead, I use only the main signal over here. So only these things I'll add it to the wave. So if you look at the wave, selected signals only will be there here. Now we give the clock to this to check for A. I just keep it 100, and this one I just keep it here as 50, and similarly for other one I keep it as 25 period. Okay, 25 period, so that I'll get different combinations. I can easily check the output. So I'm just running it. So as I run this, we'll be able to check. So for first condition, all 111, then sum is 1, carry is 1. That's wrong. Sum is all 1 1 means yeah, sum is 1, carry is 1. Then 1 1 0, then 0 1. Then we have 1 0 1, that is 0 1. Then 1 0 0, 1 0. Then here we get 0 1 1 and 0 1. And similarly we get all those 0 0 0 conditions also. So like this, by adjusting our clock, we'll be able to get all the possible combinations. That means now it's functioning as a full adder. So let us close this model sim, and now we are going to see to the similar synthesis. So in synthesis, we'll check for the netlist RTL viewer. So here we will be able to see that. So a half adder, two half adders are used, namely HA1 and HA2. So these two half adders are going to be used as a primitives. And in addition to that, there is a OR gate used here to generate the main carry, and similarly we get the sum from here. So that's how basically if you expand this, you'll be able to see that there is a carry and a sum output of half adder defined here as well internally. So like this, we can able to generate to develop a full adder using a data flow modeling. So now it is using data flow modeling. Data flow modeling doesn't require any primitives, but all that it requires is a continuous assignment statement where we assign the value to the sum net, with an expression that is A exclusive or B exclusive or C in. And similarly, for a carry, we assign carry is equal to A, A and B, or B and C, or A and C. So this is how basically we define our carry and sum for the full adder using data flow modeling. Okay. So now let us save this and we'll analyze and elaborate it. As we analyze and elaborate it, we'll check for any errors. If there is no error, we can go for a simulation, RTL simulation. So now here object C is not declared as there. Okay, so what is that error? Because I have used a scene here. So here we can use scene and here also we can use it in. Then you can save it. Once again, you can run the elaboration by double clicking or by restarting it again from the right clicking option. So once again, we'll check for the errors. No, there is no errors. Okay, so there is no error. Now we will go for simulation. So in the simulation, we just go to the RTL simulation. So in the RTL simulation, we use the model sim here and also we expand it. Now we'll expand the work. We'll be having a full ladder and we'll simulate it. So as we simulate, we'll get our required objects over here. Then we select it and we send it to the wave. So as we move this to the wave and rearranging my outputs for my convenience, then I'm passing them signals that is uh, I'll set all falling edge. So then similarly I set this also with the second signal also I set it with some 50 anything. Okay, then also for this, even for this, I set a falling so that we'll get a 0 0 combination immediately. So 50 nanosecond. Then similarly I set here with the value 25 25 and we'll put this also as a first edge as a falling edge. Now let us run this. As we run this, we'll be able to see our input and output signals. So here we have 0 0 0, then output is sum is 0, carry is 0. Then here we can see this carry is alone 1, then sum will be 1 and carry is 0. Then here 0 1 0, then sum is 1, carry is 0. And 0 1 1, sum is 0, carry is 1. 1 0 0 also, sum is 1, carry is 0. 1 0 1, that is sum is 0, carry is 1. All one combination also we get both sum and carry 1 over here. So that means it's functioning as a full ladder. Now we will close this. After closing, we will get into the netlist viewers for checking the synthesis version of this. And now we will select the RTL viewer. So in RTL viewer, now we will be able to see system has interpreted our information into a three input OR gate, the three input XOR gate, which produces sum, and three AND gates taking the A, B, and C in values appropriately, and all three are ordered together to produce a carry. So this whole module develops our full ladder, that can be viewed and checked individually as well. Okay, thank you.